Given a one-indexed array of integers numbers that is already sorted in non-decreasing order, find two numbers such that they add up to a specific target number. And then there are some details about the indices that they want us to return. The tests are generated such that there is exactly one solution. You may not use the same element twice. And then finally, your solution must only use constant extra space. And then in the first example, numbers is 2, 7, 11, 15, and the target is 9. 2 and 7 add up to the target, and they're at indices 0 and 1. But as the question says, we have to increment them by 1. And so instead of 0 and 1, we return 1 and 2. It's silly, but that's what they want. So if we ignore this weird index thing, this is just the original two-sum problem, except that the input will be sorted and we have to use constant space. So the obvious question is, how do we exploit the fact that the input is sorted? And I want to start by making specific observations about sorted arrays because that's the differentiating factor here. So let's take a look at the array from example 1. Because the array is in non-decreasing order, every element is greater than or equal to the ones before it. And then what are other obvious things? Of course, the smallest element will be on the left, and then the largest element will be on the right. And this is interesting because the smallest and the largest elements make up a pair of numbers we could examine. So my question is there anything special about the pair made up of the smallest and the largest? This is the input from example 1. And I've labeled smallest with an S and largest with an L. So if we sum 2 and 15, we get 17, which is too big because the target is 9. And I'm noticing that even though 15 is paired with the smallest number we have, the sum is still too big. So that means it's impossible for 15 to be part of the target pair. Now here's another more concrete way to think about it. Let's say that 15 were part of the target pair. If that were the case, it would need to be paired with a -6 because 15 plus -6 is equal to the target 9. But obviously -6 isn't in the array because 2 is the smallest. And so we can permanently dismiss 15 and act as if it's not even there. And to represent that, I'll just replace 15 with an underscore. And then now our new largest number will be 11. So I'll move this over. And so we can imagine that we're starting again from scratch with a brand new array that has one fewer element. And this is a really important point. You have to recognize that we can fully throw out 15. It's completely useless. And this is also good because now the problem is smaller, which means we're getting closer to the answer. Let's see if we can apply the same reasoning again. So we sum 2 and 11 and we get 13, which is too big. And since 11 is paired with the smallest number and the sum is still too big, that means it's impossible for 11 to be part of the target pair and we can safely chop it off. Again, another way to think about it is that 11 would need to be paired with -2 because 11 plus -2 is 9. But obviously -2 isn't in the array because 2 is the smallest. So I'll replace 11 with an underscore and update largest, and we're left with this. Smallest plus largest is 9, which does equal the target, and we can return. Our reasoning so far is promising, but are there any other cases? So we've thought about what happens when the sum of the smallest plus the largest is bigger than the target. We also thought about what happens when it equals the target, but we also had to think about what happens when it's smaller than the target. Here's a new example that illustrates this case. We have 2, 7, 11, the target is 18. So if we take 2 plus 11, that equals 13, which is too small. And since 2 is paired with the largest number and the sum is still not big enough, that means it's impossible for 2 to be part of the target pair and we can safely chop it off. Again, another way to think about it is that 2 would need to be paired with 16 because 2 plus 16 is equal to 18. But we know 16 isn't in the array because 11 is the largest. And so we can safely exclude 2 completely. So I'll change 2 to an underscore, and then we'll move the smallest over to 7, and then I'll completely reset this as well. Now we're left with 7 and 11. 7 plus 11 is equal to 18, our target, and we can return. So now we know what to do if the sum is smaller than the target. Just like in previous cases, we'll either get the target pair or we'll be able to dismiss one number, which shrinks the size of the problem. This means that we'll be guaranteed to make progress towards the answer at every step. This strategy will take O of n time because at each iteration, we're going to cut down the size of the array by 1 element. And then it will take O of 1 space because we just need a few variables to keep track of the smallest and the largest number still in consideration. Now that we've fully worked out the logic and we understand why it works, let's move on to our implementation. So first I want to create an index for the smallest number, and since it's on the left, we'll call it left and set it to 0. And then the largest will be on the right and it will be the last index. So numbers -1. And then I want to keep examining the pairs at left and right as long as the left index really is still to the left of the right one. And we can do that by continuing as long as left is less than right. Now I want to compute our sum. So the smallest in consideration is numbers left, and then the largest is numbers right. And then we want to take this sum and compare it against the target. So if it's equal, then we know we found our target pair and we can return. So we'll return left and right. And then we have to do that silly thing where we add 1. Now I want to handle a case where the sum is bigger. So if the sum is bigger than the target, then that means the largest number still in consideration can't be part of the target pair, so you want to chop it off. And we can do that by decrementing right. So we'll take right and reduce it by 1. And then the last case is the sum is smaller. So if the sum is smaller, then we want to get rid of the smallest number in consideration because there's no way it can be part of the target pair. And we can chop it off by incrementing our left index. So left, and we'll add 1, and then we can submit. So the code is pretty straightforward, but the thought process for getting there is pretty challenging. If you go back to the beginning, our line of reasoning started with asking, how do we exploit the fact that the input is sorted? From there, we made some observations about sorted arrays, which led us to ask, is there anything special about the pair made up of the smallest and the largest? Then we discovered that we could repeatedly remove an element from consideration. And finally, we asked, are there any other cases to make sure we didn't miss anything? And what's most interesting is that we spent the bulk of our time thinking about whether we were actually right. It can be really hard to know if an idea will really work or if you should dismiss it because it's wrong in subtle ways. The best programmers recognize this and take deliberate steps to get better at proving and disproving ideas. But this is super rare. Most people just throw stuff at the wall and hope that it works. Now, what most people do is okay at the beginner level, but will become a serious limiting factor if you want to go past that. This is why so much of my teaching is focused around helping students reason about correctness, and I try to model it as much as I can, like I did here in this video.